Today I would like to start a new subchapter, and that will be about what's now going on. Why can't we see anything on the screen here? I'm sorry, I'm having technical problems with the screen. I don't know what this is now about here. It should now show the VGA as it always does. But it doesn't. Oh yeah, now here we go. Okay, so today's subchapter is about electron counting in transition metal complexes. So first of all, why do we need electron counting? Because the number of valence electron in a complex is important for the stability and the reactivity of coordination compounds. So electron counting sounds trivial at first glance, but it's actually not as trivial as it sounds like. There are even two different methods for electron counting available. That's the so-called neutral atom method, and that's the oxidation state method. So both of them are approximately equally common in the literature. For that reason, we need to know about both of them. So let us directly go to the first method. The first method is called the neutral atom method. And the neutral atom method is comprised of 3 steps. So in the first step, you need to write the number of electrons in the neutral valence shell. And the number of valence electrons always correlates to the group number, so you can read the number of valence electrons directly from the group number. So then in the second step, you account for the ionic charge at the species. So when you have a complex anion, you add the respective number of electrons according to the charge of the complex. So for instance, if the complex has a 2- charge, then you add 2 electrons. If the complex has a 2+ charge, then you subtract 2 electrons. If the complex doesn't carry a charge at all, then there's nothing to do. So thirdly, you add the number of electrons contributed by the ligand, whereby you have to consider each ligand to be neutral. And that means that you have to cleave the metal ligand bond so that you're producing a neutral ligand, and then look at how many electrons that neutral ligand contributes to the bonding. So here is one example to illustrate this method. So here we have our cis-platinum complex. So we have 2 chloroligands and 2 amine ligands bound to a platinum. So our first task is to write down the number of the electrons of the neutral atom. So in this case, our atom is platinum atom. So we need to look into the periodic table and see in which group our platinum is, and then count the number of electrons accordingly. So where is the platinum located, in which group? No, not 8. It's actually 10. Yeah. So it's a group 10 metal. So it has 10 valence electrons. It has 8 d electrons and 2 s electrons. So that gives us 10 electrons. So the next step, we need to add or subtract electrons according to the charge of the metal. or the charge, sorry, the charge of the complex. So in this case, our complex doesn't have any charge, and for that reason, we do not need to add or subtract any electrons. Okay, and last but not least, we need to add the number of the electrons contributed by the ligands. Now, the important point here is to treat each ligand as a neutral ligand. And in order to do that, we have to think about how to cleave the metal ligand bond so that a neutral ligand results. Okay, so now let's do this step by step. So let's look at the chlor ligands first. And you need to realize here that we actually have to cleave the chlorine platinum bond in the middle to produce a neutral ligand. Okay? So only if you do this, you produce, in this case, neutral chlorine atoms. Okay? If you assign both electrons in this bond here to the chlorine, you would actually get a chloride, and that would not be a neutral ligand anymore. Okay? So in this case, you have to bond, you have to cleave the bond homoleptically to arrive a neutral ligand. So now, how many electrons will that ligand contribute? Well, because we have cleaved our metal ligand bond in the middle, the chlor ligand will only contribute one electron to the bonding. The other electron here would come from the platinum. So this is how we would count the electron. Okay. So now for the other chlor ligand, of course, exactly the same is true. For the other chlor ligand, we also need to cleave the bond in the middle. And for that reason, also our other chlor ligand is a one electron donor. So now, what about the amine ligands? So now in this case, you have to cleave the bonds heteroleptically. Okay, you have to assign both bonding electrons to the ligand. Only in this case, you're creating a neutral ligand. So the neutral ligand is in this case a neutral ammonia molecule. Okay, if you assign both of these bonding electrons to NH3, you basically create an electron lone pair here at the NH3, and that is necessary in order to make the NH3 unit neutral. Okay, so for the other NH3 ligand, of course, the same is true. Also here we have to assign both electrons to the amine ligand to create a neutral fragment. So for that reason, now our ligand is a 2-electron donor. We say that both electrons that are used to make the nitrogen platinum bond are coming from the platinum. Sorry, coming from the nitrogen. Okay, so now we can just sum up overall the electrons that we have counted so far, and the sum gives us the overall valence electrons of the complex. So we say that for the platinum we have 10. So we do not have a charge, so that doesn't add or subtract any electrons. The two chlor ligands contribute 1 electron each. That gives us overall 2. So the two nitrogens, or the two amine ligands, they contribute 2 electrons each. And that gives overall 2 times 2 is equal to 4, and 10 plus 2 plus 4, that gives us overall 16. So we can say that this complex here is a 16 valence electron complex. So we have counted thus far with a neutral atom method. Now let us count the electrons using the other method, which is the oxidation state method. So the oxidation state method, of course, has to arrive at the same number of valence electrons. It's just that we count the electrons a little differently. And the oxidation state method is named oxidation state method because it involves the determination of the oxidation state at the metal. All right, so now which steps are involved here? So firstly, again, we write down the number of electrons in the neutral atom valence shell, and again, that corresponds to the group number. So the first step is the same as in the neutral atom method. So then what do we do in the second step? Now the second step is different. In the second step, we determine the formal oxidation state of the metal. Okay? And that will either reduce the number of valence electrons if the metal has a positive oxidation state, and that's mostly true, but not always so. In some cases, the metal can also have a negative oxidation state, and if this is so, then we add electrons. Okay. Now, in the last step, we then add the number of the electrons contributed by the ligands, okay? Whereby in this case, the ligand does not need to be a neutral ligand. It can be a neutral ligand or a negatively charged ligand, okay? So how do we determine the number of the electrons? In this case, we always cleave the metal ligand bond heteroleptically. That means that we assign all the electrons in the bonds to the ligand. And then we count just these electrons. And that's the number of electrons that are contributed by the ligand. Now let us apply these rules to exactly the same example that we discussed previously. So the first step is the same. So again, we look at the platinum first, and the platinum is still in group 10. So it will contribute 10 valence electrons. But the next step, we now have to determine the formal oxidation state at the metal. So how do we do this? Well, we cleave the metal ligand bonds all heteroleptically. Okay, we assign all the bonding electrons to the ligand. Okay, so in this case, we really treat our complex as a species in which we have only dative bonds. Okay, where the ligand contributes all the electrons that are being used for bonding. And then we look at what are the charges at the ligand. Okay, and then we look at the metal and ask ourselves, well, what charge does the metal need to have so that the charge at the complex, the core charge at the complex resides? So if we do this, then we assign these two electrons to the chlorine and these two electrons to the chlorine. Okay, so that makes these chlorines chloride anides. They have a negative charge each. So that gives us two negative charges at the ligand. So next, we do the same with the amine ligands. Now, as we assign both electrons here, the bonding to the amine ligands, we create neutral fragments. So they don't carry a charge. So we have overall two negative charges at the ligands. Now you see that the complex is overall neutral. So for that reason, what is the oxidation state of the metal? +2, correct. So now we have determined the oxidation state of the metal, and we add or subtract electrons accordingly. So in this case, we have to subtract 2 electrons from the 10 electrons that we previously counted. So that means that we're currently standing at 8 electrons. So last but not least, you now have to add the number of electrons contributed by the ligands. Okay, so now you have to keep in mind that we have cleaved the metal ligand bonds heteroleptically, so that you would assign all the bonding electrons at the ligand. And that, of course, now means that the two chloro ligands contribute 2 electrons each. Okay, both bonding electrons came from the ligand. So now for the amine ligands, the same is true. Both bonding electrons came from the amine ligands. So now we have determined all the electrons and determined the number of the electrons, and you can just sum them all up. So we have here that actually it should be a platinum, not a palladium. 10 valence electrons coming from the platinum. So then we subtract 2 electrons because the platinum is in the oxidation state +2. And then we add 2 times 2 is equal to 4 electrons coming from the ligand. And we add another 2 times 2 electrons, another 4 coming from the amine ligands. So that gives overall 10 minus 2 plus 4 plus 4 gives also 16. Of course, the oxidation state method and the neutral atom method both have to arrive at the same result. They just use a different algorithms to arrive at the same result. So now, which method you like more is basically personal taste. In my opinion, the oxidation state method has the advantage that you really treat the metal ligand bond as dative bonds, while not necessarily that is the case in the neutral atom method. But the neutral atom method has the advantage that you do not have to think about oxidation states. Okay, so you can omit that step. So again, it's really personal taste what you prefer. I might slightly prefer the neutral atom method, but if you like oxidation state method, that's totally okay. But you need to be able to apply them both. Okay, now let us practice this a little bit. So oftentimes the most complicated step is to determine how many electrons the ligands contribute. So let us practice this a little bit together for a number of different ligands. So for instance, when we have a very simple hydride ligand, which can be part of, for instance, nona hydrohydrogenate to minus anion. We have encountered this anion previously when we discussed the coordination numbers. Remember, that was an example for the coordination number 9. Then we can first determine what is the charge at the ligand when we use the neutral atom method. So this is a very trivial question because the neutral atom method mandates that the charge at the ligand is 0. So now, having determined that or kept that in mind, we can also determine the charge at the oxidation state method. Now, in this case, you need to cleave the bond heteroleptically. The oxidation state method always does that. So what charge does then the ligand have? Virtual students are also invited to provide answers. All right, we have one suggestion in the chat. -1. Yeah, that is correct. So we have here the metal hydrogen bond that contains 2 electrons. So we cleave the metal hydrogen bond heteroleptically so that both electrons are being assigned to the hydrogen. And that creates us an H minus anion with a 1- charge at the ligand. Okay, so the charge is minus 1. All right, so now we have determined the charges. Now let's look at how many electrons this ligand contributes according to the neutral atom method and the oxidation state method, respectively. Okay, so number of electrons donated in the neutral atom method is now what? We have to cleave the bond how in order to create a neutral fragment? Sorry?
Wow.
Yeah, so we have to cleave it in the middle. Yeah. So we say one electron comes from the hydrogen and one electron comes from the metal. So we have one electron contributed. Right. So now what about the oxidation state method? So we previously said, well, we cleave the bond heteroleptically, as we always do. Oxidation state method. So how many electrons does the ligand contribute then? 2, correct. Okay, we have an H- ion, 2 electrons, which contributes both electrons to the bond. Okay, another example, a fluoroligand. An example for that would be, for instance, hexafluoroplatinate 2-. The charge in the neutral atom method would be necessarily 0. It's always 0. So what would be the charge, however, with the oxidation state method? So now, again, with the oxidation state method, we always cleave the bond heteroleptically. So if we do so, what is the charge of the ligand? -1, correct. We assign both electrons to the fluorine. That makes the fluorine a fluoride with a 1- charge. So now, how many electrons are donated by the neutral atom method? So now you have to think about how you have to cleave the bond so that a neutral fragment results. So in the case of the platinum fluorine bond, how do you have to cleave it so that a neutral fragment results? Sorry? So homoleptically in the middle. Okay? Yeah, that's correct. If we do so, okay, we create a neutral fluorine atom. And how many electrons will this fluorine atom contribute? It will contribute 1 electron, right? Okay, so now what about the oxidation state method? So the oxidation state method, well, as we did already previously, we have to cleave the bond heteroleptically. So that creates a fluoride anion. Okay. So now how many electrons are contributed in this case? 2. All right. Good. So a few more examples. So let us go to bridging halogenide ligand. Okay, so they cannot only be counter, they can also be bridging. So an example is, for instance, this rhodium complex with 2 rhodiums that are being bridged by 2 chloroligands. Okay, so in this case, the chloroligand doesn't utilize only 1 electron lone pair, but actually 2 in order to achieve that, the bridging function. So what is the charge of the neutral atom method? 0. It's always 0. Think about what is the charge in the oxidation state method. -1. Let us see if this is correct. it is actually correct. So in this case, we again cleave, as we always do, the bonds heteroleptically. So we assign all the electrons in this case 2 bonds to the ligand. Okay, so then again produces a chloride, and the charge of chloride is -1. Okay, so now what is the number of electrons donated in the neutral atom method? So in order to determine this, you first have to think about how to cleave the bonds. And in this case, you have a more complicated task because you have 2 bonds to cleave. So you have to assess each bond individually. So what would you do?
So would be 2. Would be 2.
How would you cleave the bonds? Both of them?
Yeah.
That's not quite right. You actually have to cleave one homoleptically and one heteroleptically. Okay? Because only then you arrive at the neutral chlorine atom. If you cleave both of them homoleptically, you would have only 6 electrons around the chlorine. You would have actually chlorine plus. Okay? So one needs to be cleaved heteroleptically, the other one needs to be cleaved homoleptically. So, how many electrons will then be contributed overall? 3, correct. So overall, we have now 3 electrons contributed. So the number of electrons donated in the oxidation state method is what? You have to cleave all the bonds heteroleptically. So that produces chloride ion, as we previously determined. So how many electrons are being contributed in this case by the ligand? 4. Yeah. Okay. Another example, an alkoxide ligand. So an example for that would be, for instance, the iron tetraoxide 3-. So what is the charge at the neutral atom method? Well, it's always 0. What is in this case the charge in the oxidation state method? -1, yeah. So why is that so? Well, we have a metal oxygen bond in this case. So again, we have to cleave the bonds heteroleptically. So that assigns these 2 electrons to the ligand. So as a result, we have formally a negative charge here at the oxygen element R or minus, and the charge is -1. So now let's look at the number of electrons donated. In the neutral atom method, how many electrons are being donated? How do we have to cleave the bond? That's always the first step. One electron, yes, because we have to cleave the bond in the middle here, homoleptically. The one electron we say belongs to the metal, the other one belongs to the ligand. Okay, and that is the electron here, the ligand is donated, so we have one electron. What about the oxidation state method? So we previously said we have to cleave the bonds heteroleptically, and then we assign both electrons to the ligand, and these are the electrons that are being donated. So overall, we donate 2 electrons. Okay, one more round of examples. We have a carbonyl ligand. Carbon monoxide is a ligand. So an example for this is, for instance, iron tetracarbonyl. In the neutral atom method, the charge is 0. So what is the charge in the oxidation state?
Zero.
0, yeah, that's correct. Why is that so? Well, we have a metal carbon bond with 2 electrons. And now we need to cleave the bond heteroleptically. So we have to assign both electrons here to the carbon. Okay, and that produces a neutral CO molecule. Okay, so remember that neutral CO molecule, the carbon and the oxygen do have formal charges. Yeah, so the oxygen has formally a positive charge here, and the carbon has formally a negative charge here. But overall, the molecule is neutral. Okay, so therefore the charge is 0. So now let's look at the number of electrons donated in the neutral atom method. How many electrons are being donated? No. So how do you have to cleave the bond so that you produce a neutral molecule? Sorry? Homolytically? No. In this case, you have to cleave the bond also heterolytically. Okay? So in this case, you need to assign both electrons to the ligand, because only then you produce a neutral carbon monoxide molecule. Okay? So it's not that in the neutral atom method always you cleave the bond in the middle. Sometimes you have to cleave it differently. And the carbon ligand is one example. So now if you add both bonding electrons to the carbonyl, how many electrons will it then donate? Two, correct. So now what about the oxidation state method? How many electrons are contributed in the oxidation state method? Also 2, correct. Because in this case, well, we cleave the bond just the way we have cleaved it in the neutral atom method. So we assign these 2 electrons to the CO, and because of that, our CO is also a 2 electron donor. So in this case, no difference between the neutral atom method and the oxidation state. Okay, one last example. So here we have a somewhat exotic ligand. So this is the isonitrile, it's an isonitrile as a ligand, where we have here an electron lone pair, actually it's carbon, that can be donated. So formally in an isonitrile, the carbon here has a negative charge and the nitrogen has a positive charge. But this gives overall a neutral molecule. So there are also complexes with this ligand. So for instance, penta butyl isonitrile complex iron. Okay, charge using the oxidation neutral atom method. Well, that is always 0. What is the charge when we use the oxidation state method? Plus 1? No, it's actually 0. And the reason for this is that we have, well, here the metal carbon bond, and we have to think about how do we have to, we have to, of course, in the oxidation state method, we also always have to keep it heterolytically. So we have to assign both electrons to the carbon. Okay. And then we produce a neutral molecule. So while, like I said before, the formal charge of this carbon is -1, we have here the nitrogen, a formal charge of +1, and that gives the neutral molecule. So overall, the charge at the molecule is 0. Okay, so now what about the number of electrons donated? First, let us look at the neutral atom method. 2, that's correct. And why is it so? Because in this case, like in the example above, we have to cleave the bond heterolytically. We have to assign both electrons to the carbon. Only then we can produce a neutral isonitrile molecule. So now because of that, our isonitrile molecule is a 2 electron donor. It donates exactly these 2 electrons. So now, what about the oxidation state method? Also 2, yes, correct. Because we also have to cleave the bond heterolytically. Therefore, these 2 electrons are also formed. So also in this example, we do not have a difference between the oxidation state method and the neutral atom method. All right. So now, like I said before, electron counting is important because the number of electrons allow you predictions with regards to the stability of a complex. And there's one important rule in this context, which is the 18 electron rule, which says that coordination compounds tend to be the most stable when they have 18 valence electrons. Okay. If the number is not reached, then we say that the species is coordinatively unsaturated, and it tends to add more ligands. It also has a tendency to be reduced because also by reduction, it can get more electrons and reach the number 18. So those coordinatively unsaturated are therefore associated with a higher reactivity. Okay. So now, if we have more than 18 electrons, then we say it's coordinatively oversaturated. We can also predict the reactivity that results from that. So such complexes tend to lose ligands, and thereby also losing electrons, reducing their number of electrons. They can also usually be easily oxidized. So the 18 electron rule is called a rule and not a law because there's a significant number of exceptions to it. And when these exceptions occur, we can, at least in some cases, rationalize why they occur. So they are particularly common for group 3, group 4, and group 10 metals. So for instance, this complex here, this titanium complex, does not have 18 electrons. So we can briefly apply what we have just learned in order to verify how many valence electrons this complex actually has. So we could choose either the oxidation state or the neutral atom method. To do that, let us maybe, for instance, choose, for this example, the neutral atom method. So applying this method, we first would need to determine what is the number of valence electrons in the metal when the metal is considered to be a neutral atom. That can be derived from the position of the titanium in the periodic table. 4, correct. So titanium is in group 4, therefore titanium contributes 4 electrons. Okay, the next step would be, let's look at the charge at the complex. So in this case, the complex is neutral, so we do not have to add or subtract any electrons. We can directly go to the third step and now count the number of the electrons that are contributed by the ligand. So we can now apply what we just practiced again. So how many electrons would come from these ligands in the neutral atom method? Also, virtual students are invited to make suggestions. 2 each. So how do we have to cleave the bond? In this case, the titanium carbon bond to create a neutral fragment. Okay, maybe let's do this. Let's do this together. So in this case, we have to cleave the bond in the middle. Yeah? Because then we are creating a radical, and I can just write it. C H to phenyl. Okay, which has here this one radical electron. And of course, that's a non-neutral species. Yeah. If we had assigned both electrons to the carbon, that would have been an anion because the carbon would be surrounded by 5 electrons. Yeah. So therefore, each ligand contributes 1 electron. That gives 4 electrons in addition. So now overall, we have the electrons coming from the carbon. So coming from the metal, these are 4. So yeah, in this case, I'm applying to the oxidation state method. So the oxidation state, by the way, would be +4. Okay. So we would have to reduce 4 electrons, and then the ligands would contribute 2 electrons. Yeah, because we would, the oxidation state method would have to cleave the bond heterolytically. Okay, but in the neutral atom method, we would not need to subtract 4 electrons here. Okay, so only 4 electrons overall would come from the ligands. 1 electron per ligand. So this gives us 8. So now that's of course far less than 18. So obviously it's a gross violation of the 18 electron rule. And we can think about, well, why couldn't that complex adhere to the 18 electron rule? And the answer is that, well, such an early transition metal has very few valence electrons. So it would add a huge number of ligands to achieve 18 electrons. And that would just get to unreasonably high coordination numbers. Especially when we have the biligands like here. So your complex then does next best. So in this case, the titanium chooses to have 8 electrons. We could maybe explain this by the fact that we have a titanium 4+ here, that's the D0 species. So in a way we can say perhaps you can only consider the S and the P orbitals the valence electron, and the 8 electron rule holds. And for that reason, the complex chooses 8 valence electrons. But this is surely somewhat oversimplified argument. All right, then here we have a 16. Sorry, here we have a group 10 complex, which is very similar to the platinum complex that we looked at previously. So in this case, we have again 16. We have actually 16 valence electrons because the metal contributes 10, that's palladium. And then when we apply the neutral atom method, the charge is 0. So the 2 chloroligands contribute 1 electron each. So that's 2. And then the amine ligands, they contribute 2 each, which is 4. So this gives 16 valence electrons. Now in this case, we could not argue as we previously argued, because group 10 transition metals have 10 valence electrons. So they do not have to add a lot of ligands to get to 18. In this case, we can argue that we have a D8 ion, and our complex is therefore square planar, and square planar complexes tend to prefer 16 valence electrons over 18 valence electrons. Now, why do they do this? At this point, we don't understand this yet. We would need to look more closely into the bonding of such a square planar complex in order to understand why the 16 electrons are in this case preferred over 18 electrons. And that leads us then to the next chapter in this course, which is about bonding and coordination compounds. But our time is over, so I will stop at this point. And on Monday, we'll have the exam, so we'll start a new chapter about bonding in coordination compounds on Wednesday.